We are going to pick up with where we left off on Thursday. We had we're doing that MATLAB example where we were composing the transforms into a single matrix. And I think we were starting to get to those relevant, good questions is, okay, that's kind of translating and scaling stuff. What does that mean for actually classical viewing of our 3D scenes? And that's what we're going to talk about starting today. We'll probably have to finish that up by Thursday, even a little bit bleeding into next week. But I did want to take the time, and I won't really be putting the teams on the spot as such, but everyone submitted their project proposals, and I have them here. And I may ask a question or two, but first off, I'm happy that everyone did it. So everyone completed the assignment. My first blush response to all of the proposals is, you're good to go in general. So I'm not going to be asking any team to start over or anything like that. There's no issue with that whatsoever. I may have a couple quibbles, mostly just about rubrics, and I'll provide that feedback formally on Canvas. Hopefully today would be my goal. Your feedback in Canvas may just be, okay, that may be the only feedback you get, but that's fine. That just means it's time to, once you kind of get going with MP4, to get started on this. And I think, for better or for worse, the nice thing here is I think for several teams, you may be able to even start on your projects now, because it's directly related to what you're already having to do for MP4. So whether you accomplish any of your goals for the project in the process of doing MP4, you may start at least, leaving some stubs in the driver for stuff will be project calls that you'll need in the driver, or thinking about what additional registers you may need in this or that module. So you can just start a little bit of that work since you're already doing and dealing with a lot of the same components here. The files weren't labeled necessarily, but this is Aiden Shreyas and Sid, and looking at your line rendering and anti-aliasing. I didn't have I looked through it, and it looks fine to me. My only thought would be, any feedback I would give is, the rubric is fine. You may want to give yourself, there is a slight 50-50. This would be also 50 points. It's just not labeled here, but that's just a typo. I'm not worried about that. You may want to consider giving yourself some credit as a team for the demo side of what software functionality you would be showing off. I was just thinking you do lines, and okay, you've rasterized a line. Are you going to be happy with that end result? You know what I'm saying with regards to that? So maybe one person on the team can also think about what's a nice and cool thing that can be done with lines that would make a nice GL lines demo, and possibly also for anti-aliasing as well. But for that, I think we saw, it's a jagged triangle and it's a smooth triangle, and you're just kind of showing the difference. So for there, it doesn't have to be too fancy. That would be my only suggestion. It's possible that can go into bonus as well. I know that as you work on this, you'll have lots of different types of individual lines and line loops as your testing applications, but having a demo application I think would be nice as well. The other thing I saw is you'll have this component which is a separate anti-aliasing unit before render output.
I haven't thought about that.
Yeah. Okay.
Maybe that's not where it would go.
I think render output might just be able to handle it. It might. I could think about that a little bit because it does depend on the order in which, basically the frame has to get rendered to this non-display buffer, this 4x resolution frame buffer, and somebody now has to tell another unit that now it is time to average the results together. It has to. I think the way we are doing things, in which it's a single fragment shader, so you're getting just a single fragment at a time. That anti-aliasing has to happen after the entire frame is rendered. In practice, that's not the case. You would have a fragment shader that's responsible for 4 fragments at a time, and you have them also potentially tiled together depending on the underlying architecture. So the anti-aliasing can happen right there, but for us, after the fact would be fine. So just you'll have to think about that anyway and get that working. And so it's also kind of nice and separable that they can't break your stuff and vice versa is a nice thing to have here. So it's kind of separable in that point, and I think this will be great. This is group 4. These are just open in random order. Which one's group 4 again? Okay, great. Classic lighting model, Fong Garage shading, lighting. This looks great. We just haven't covered it in class yet. We are about to cover this in class. There's lots of material on it, so you can kind of get ahead of class and learn what you need to learn for how to do this. There was some discussion in here, I recall reading, about whether you're going to do it per vertex or per fragment, the lighting. And I guess I would say the funny thing about our architecture is there's a performance difference, obviously. One is going to be exceptionally slower than the other, but the cores are kind of the same otherwise. So I think you do one, you kind of get the other one for free, effectively. So that's okay. So I don't think you don't have to make it a separate design goal or give yourself extra credit for getting it in the fragment shader. You may want to do it in the vertex shader, even though it'll make the triangles look very meshy, right? Because it'll be obvious where the lighting changes. But that's also the nicest way to visually test that it's working well. So, but otherwise, the goal would be to do ambient. Should be okay, right? Ambient, you could do today if I asked you to do ambient lighting, right? That just add a constant to the color, or have some material properties potentially, but otherwise add a constant to the colors. And material properties would oftentimes be per vertex, but you may just have to have it, well, you could do it one of two ways. You could have it be per vertex, and then you'd have to just get rid of the texture coordinate attributes, or just have it be a constant per render, another uniform, and then you can have both texture mapping and lighting, because you'll need to have the normals as encoded per vertex to be able to do the specular highlights. Otherwise, that should be okay. The only thing I would suggest that you do, unless you already have, and that's fine, conceptually this is great. What I would like you to do is to take a look at the Flex Seal basic lighting per vertex lighting and see what gets generated via the assembly for that, and see, okay, how many of these instructions do we have, how many do we not have? And then I think that might lead to possibly a reshuffling of what you give yourself credit for. I mean, it's okay to give yourself ambient lighting implemented with needed hardware updates. I just don't think there's any needed hardware updates for ambient lighting. So, congrats, you've done it, right? But then you may want to look at, well, there's actually 3 complicated instructions we have to get working. They're all doable, but they're each going to take some time, and you may want to give yourself some points, because oftentimes, even if you don't have the instruction perfectly working, the end result from a lighting model calculation for the Phong model, which is all just kind of a hack anyway, may still look pretty good. So you may be able to have some compromise support there. Runtime directional light source, just to give an example where you may want to take points and move them somewhere else. I think a light source is just another uniform. I don't think there's anything hardware-wise for light sources based on how those are typically implemented. It's dynamic in the sense that it changes once per frame, where you have a light position, possibly some light attributes, so it's not just a white light, it's a blue light or something like that, and those would just be Vec4 uniforms that you would specify, and so that just loads from memory from the shader. So that may already be done for you as well, whereas the effort to get diffuse and certainly specular may be a certain number of instructions, and it may be a decent amount of work. So my feedback to you won't necessarily give you the answer to that, but it may be look into it a little bit more. Tomorrow in lab, while you're waiting for a build to finish or something, look into that output and get a better feel for, okay, here's these additional instructions we'll have to support, and then refactor the rubric accordingly. And then otherwise, should be doable. Should be something you should be able to get done. So the technical debt would be, I don't know where you are with that, but you would definitely want to get the cube working from MP3 first for that matrix vector stuff, because you need to get all that stuff working for this to work too. Otherwise, looks great. Cheyenne's here, Joel's here, Long is thinking about coming. This is texture mapping, right? So advanced texture mapping. And as a preview, I don't think too many teams will get texture mapping kind of fully working by when I want us to do MP4 demo day. Well, first off, it's kind of ambiguous in the MP4 document. How much texture mapping do you really have to get done? There are so many variables or options or knobs or things you can tweak when you do texture mapping, and I kind of leave it up to you to say, get this basic version working. So taking that and then also getting a more advanced version working, I think would be a great goal for that. You do talk somewhere about 3D texture mapping, but maybe I hallucinated that. I thought I saw to more complex 3D objects, but you don't actually say 3D texture mapping, so that's fine then. The thing you will have to get if you have actual 3D objects is you'll have to get perspectively correct transformations working. We're going to start talking about that today. It just requires an additional division operation. As I was thinking about how I was going to implement that, even my demo code doesn't do that properly for this class. I would just do it in the vertex shader itself. So you apply the transformations, you then do the perspective transformation, the division yourself just in software. From a hardware perspective, it's the same either way. You have to support a division unit, and then you get that to work. You do say here 3D textures, which is a thing, but then looking at the rubric, it doesn't really speak to that as much. So my feedback will eventually be, okay, now the idea is fine, the idea I approve, be a bit more specific with what you want to actually accomplish. Somewhere it said multiple texture units as well as like an option here. And that's certainly a thing, it's a valid thing to do as well. For us though, with regards to where the bottlenecks are in our system and the amount of hardware resources we have available, it probably doesn't make sense to have multiple texture units. I have to think about that a little bit more, and I will think about that a little bit more today, that for a single fragment shader, you're going to have multiple textures applied to it, so you'd want to have multiple texture units. That would be nice. I got to think about whether that would work well, what other little headaches that would create, to what extent do we have that supported in the driver for multiple texture units. I got to think about that a little bit more, and then I'll want the team to think about that a little bit more, because you do want multiple textures applied here, but you may be able to do it just with a single texture unit, because it is kind of a sequential operation for how we're implementing things. Otherwise, I'm excited to see that. That was your TA Jeremy's group did something very similar last year and was able to get it working pretty well. So the Zambriano cube was the output of that. Andrew Gotham and Maisie exploded, you said this morning. Didn't explode. Sorry, I just heard the word explode and I figured it was in the positive. So Maisie, if you're watching this video, as we all know you are, we miss you. Come back to us in one piece. So bump mapping you talk about, and that was her idea that she was excited about, and so I think that would be great. I am guessing your project is going to have a ton in overlap with just the lighting team. Because I did have to look at it a little bit more, because I had thought of a version of bump mapping in which you were manipulating basically what they call tessellation shading, and that would have been very difficult. But if it's just bump mapping that is changing the normals of each of the fragments that are getting generated so the object looks more bumpy, right, basically, that should have a ton in common with what the group who was doing just, maybe per fragment lighting was wanting to do. And so for the same reason, I think it's great and it should work. Just to give an example of the kind of homework I still want you to do, additional ISA instructions may be necessary. I agree. I think that's an answerable question. Put in a valid bump mapping lighting shader and see what comes out. See if it crashes, see if it actually generates anything, but then see what comes out and see for these instructions, what additional work will it require. Demos are probably going to look a little cooler than your actual demos will be able to be. And we have not talked about this at all, but the idea would be that you have some sort of like normal map, right? And so it is a type of texture that gets applied, but you're not applying the texture directly, right? You're not wrapping paper around the object. You're instead taking that texture, which is describing a displacement of what the normals could be, and you're changing those normals by that relatively small amount is what you're planning on doing. So the shader code for that shouldn't look that different than just getting lighting to work. So you have to do a texture lookup, then the normal calculations for your diffuse and specular, and then you're just doing that on a per fragment basis. So I feel like you should be able to get that to work. And it's okay to work with that team as well. You're not like directly sharing code, but as they get certain things to work and have discussions, I'm totally okay with that also. And I think recognizing that that's the case is important, that you have to get like the basic stuff working first, and then you can add in this additional wrinkle to it. I don't know what steep parallax mapping is. I should possibly, but I don't know the term steep parallax mapping.
Yeah, that was Maisie was researching that a little bit, and I think it's pretty much a different way of doing the bump mapping of calculating like the change in the normal.
Okay, but either way, it's taking a texture value, doing some math with it, and applying it to the normal to manipulate the normal. So you still have to basically get this work. I would argue, maybe this should be 50. I mean, it's up to you guys, and you'll be fine either way, right? Maybe that should be 50 points, because that's pretty good if you get that working. And the visible differences would possibly require a software demo that you haven't currently given yourself credit for. So that could be where you could, give yourself credit also would be, well, if there is an interesting difference between this and this, you have to have a demo that illustrates the difference, I guess, right? So give yourself credits. If you have to write an application that will itself take a little bit of time, give yourself points for it. But otherwise, this is great. So, the lighting is a little bit on the, aggressive side in terms of the amount of work you're going to have to do, but not absurdly so. So I think, the teams will be okay. There's 2 teams working on it. So, share some best practices, share successes, commiserate with failures along the way. And, I think you'll be able to get it done. Anti-aliasing, I think, will be great. Line rasterization, I think you're going to find it annoying more than anything else, depending on the approach you take, because it feels like, hey, we already have triangles working, why are lines being difficult? But it should follow a similar approach. Of course, you can rasterize lines as just small little rectangles if you just want to do it that way. And anti-aliasing should be able to work. And then texture mapping with multiple textures. There's a little bit of unknown to me there in terms of what does the driver and the compiler infrastructure provide for that, but I expect you to be able to get that done as well. So my advice to everyone is, yes, I'll be providing a little bit of Canvas feedback today, hopefully. I will then expect eventually every team to kind of upload a new just rubric is all you need to upload, not the full document. There's not a huge rush on that, but before the next demo day, I'd like you to upload that. Before you get started in earnest, I'd like you to re-upload that. But otherwise, you can get started. And as you're working on MP4, it's relating to everyone but the anti-aliasing proposal, I guess. As you get started in more earnest in MP4, you can start to think about, okay, there's this we have to do for MP4. Let's start thinking now, what does it mean for our project? What extra things do we have to explore for our project? But this is great, so I'm excited. Happy to see everyone get started. I may ask you in a couple weeks to give status updates of how this is going. As you know from these MP assignments, as we were talking about before class started with a completely different course, you can't do this last minute either, right? You're not going to be able to weekend this and get this to work, because that's just not how these type of projects work. It does require kind of steady, progress along the way, conceptual sprints, implementation sprints, and just being kind of honest with each other that this is a very busy time of year for all the other projects you have. Some of you are graduating, this semester and all that entails. You just got to find the time and treat it like a lab. We'll have basically 3 Wednesday sections where you can work on this. That's probably not going to be enough for any of these projects. That's a good synchronization point. That could be a sprint that the team has. The tricky part is also, I think, not that you've really been asking me tons of questions. Everyone's been able to kind of figure it out, or with Jeremy's assistance. Some of the questions you may have for this, I may not have very clear answers. I may have high-level suggestions, but I don't necessarily know. I don't think the errors you're going to see are going to be new. It's going to be Vivado errors or driver errors or things like that. But when you run out of space, for example, which may happen when you start adding all these resources, it's a little bit uncharted territory for us. But persevere. Don't give up when things just look like they're going to fail. And I think focus on your rubric. Focus on what is a reasonable, successful project. That doesn't mean you got 200 out of 200 or 300 out of 200 with all the bonus points, but you got something that you're reasonably proud of that kind of fits the general theme of what you're proposing and gives yourself credit based on how you assign your rubric. And when you look at your rubric one more time, think about, if it truly explodes on us, what score will we get? And hopefully that's at least 100 points or something with a true explosion result there. But I don't expect that to happen. I think everyone will be able to get something working. And certainly for the 3 that involve more on the fragment shading side, MP4 is kind of important for you. It's not wasted effort at all to do MP4 and to do it really well because it's just points for your project as well. Any other project-related questions before we kind of forget about it between now and the end of the semester? Okay, awesome. Well, like I said, I'm excited about it. So let's start talking more about the transformations. We already kind of introduced somewhat, I think, abstractly last week, and then what does this mean for actually, rendering 3D scenes, right? The whole point of this course. And a common mistake when working, I would say, with OpenGL or reasoning about a scene is to do that conversion to 2D too early, like conceptually. To start thinking about very early on in the process how that final image is going to appear on a 2D screen. That's been okay for us because we've been doing primarily 2D applications, but once now our code is going to have some 3D element to it to be meaningful here, we really have to start, and this is just general good advice for doing graphics programming in general, but for us specifically as well, to attempt to try to visualize the 3D space and the series of transformations that are going to be eventually applied to go from 3D space to eventually our pixels on a screen. Some of those steps we're already aware of, others we're learning at a high level, and then soon now we're going to see what those happen to be in practice. Ultimately, this whole first step is just going to be a matrix or series of matrices. So mathematically, we already kind of have a feel for that. There's a couple different flavors of that matrix we'll talk about when we look at things like perspective viewing of a scene, but ultimately, we can represent them all by a 4x4 matrix. So there's going to be a series of those matrix vector multiplications going on here. There's then that second step that we've kind of covered, at least in the abstract, but we won't be implementing in hardware, and none of your projects will be implementing in hardware either, which is the clipping stage. So we're going to be doing all of these kind of 3D matrix operations to transform, to rotate, to scale, translate our objects around. Eventually, we then determine what is our valid viewing space, and we remove the objects that aren't within that space, the clipping and the potential culling here as well. And then finally, only at that point do we effectively then drop our Z dimension. So we stay in 3 dimension up until the very end here, when once we do that viewport transformation, our values in these device coordinates get converted to effectively pixel coordinates in our frame buffer, and then we use that depth information to determine not a location, but now whether or not it should be blended or whether it should be thrown out entirely because it's farther away here, given our transformed depth coordinates and our pixel coordinates that we have here. So in practice, we actually stay here quite a long time. With the way we've kind of built up, starting with just pixels and starting 2D and then finally kind of almost shoehorning 3D stuff on top of it, it doesn't really feel that way. But the vast majority of the lifespan of our vertices is in that 3D world, and we really are going to drop that final dimension at the very last point in which we need to do it to store into a depth buffer to do that depth buffer calculation here. Part of where the confusion I think can sometimes come into play is that we were doing that viewport transformation from day one, because we did need to get things in our pixel coordinates to get anything to display in a frame buffer. But that viewport transformation more generally can also be thought of as an additional matrix calculation that's performed on our coordinates. Because it's a very specific type of transformation that is effectively just a scaling here in X, Y, and Z, we don't usually implement it as a matrix. We have that standalone unit that's doing that scalar multiplication for us, but it is effectively an additional matrix that gets applied to it. And then again, where the confusion can also come in is because for reasons of just limiting how much hardware we're implementing, because we aren't doing our clipping of geometry, we have had to take a little bit more care from day one in terms of the specification of our 3D scene. Because if we specify something that falls outside that range of what we want to see in a default viewing coordinate system here, the end result would be like wrapping of values over and potentially nonsense-looking geometry. We then are our own clippers in terms of how we specify our geometry, which is not normally the case. That's a limitation of this class, not a limitation of the concepts that we're exploring here. So finally, we can introduce to some level the textbook version of the synthetic camera model. What does it mean to have a 3D scene? I think it's important to mention that, some places will view this as, or represent this as like the human viewer. That's also fine. So there'll be a picture of an eyeball there and not a camera. But there is no camera, there is no eyeball. This is a synthetic way of reasoning about a 3D scene and how it will eventually become 2D. There isn't a camera per se. There is something that is meant to represent what could be a camera and how, in the quote-unquote real world, we visualize a scene before taking a picture of it, which is also a 3D to 2D transformation, right? So what we have in our synthetic camera model are the various objects we want to potentially view. We are then going to have the actual viewer here, and then potentially things like light sources and textures and things of that nature. Our kind of old school focal plane camera has a certain lens associated with it. It captures the light as it's entering into the lens, and then given a center of projection, we have an actual projection of that objects in the scene that are visible within the focal range of the lens onto our center of projection here. And it's going to use kind of basic trigonometric concepts to say, given our specification of geometry, what should the final scene be viewable in our final image plane here. Just remember from last week, I wanted to bring this up again, our homogeneous transformations, similar to how we had 2D XY, and we were able to kind of add a synthetic third dimension W to allow us to do all matrix operations for our translation, scaling, and rotations. We do the same exact thing for our 3D geometry. So of our 3D point X and X, Y, and Z, we also have this additional dimension of W, which becomes impossible to kind of visualize now when we're limited to visualizing 3D things here. But our point X, Y, Z can be considered a point in a 4D space for which we have kind of a hidden or artificial parameter W here, which by default we set to 1 for all of our geometry. If we do that, you can think of that again as a mathematical trick, right? What that allowed us to do when we were looking at that last week was to represent all the transformations as just matrices, including the translation one. So it turns out, because we had this additional dimension, the way our linear algebra works is we can just do our plus dx plus dy plus dz, representing that using the fourth column of our matrix, and then everything can then get encoded as a single matrix there. Whether we decide to do a lot of matrix multiplication in hardware or a priori kind of on the OpenGL side doesn't really matter as such, as what matters is the fact that they can all be represented as a matrix for a single matrix vector multiplication at the end of the day. That gives us all the nice properties of composing our transformations and building a final matrix at the end of the day. So this is in some sense a review from last week, but just with an additional dimension, so it's got a little bit more going on here. So we have our translation now with that fourth W dimension here. We can encode that directly via matrix vector multiplication. Same with our scaling. We can independently scale in our X, Y, and Z dimension by setting the values corresponding to that on the diagonal. We can do our rotations, and we didn't go into full derivations of that, but by converting the polar coordinates and thinking about the rotation of a certain addition of an angle from the initial polar coordinates theta here, it looks a little bit different, only that there's now 3 different axes we potentially would be rotating around. Which values we're changing in X, Y, then relate to which one is not changing, or Z in this case doesn't change when we rotate around the Z axis. Y doesn't change when we rotate around the y-axis, and X doesn't change when we rotate around the x-axis. And again, we can compose all of these matrices by just multiplying them together. The order in doing so matters. So rotating something around the z-axis, which I'm going to have trouble visualizing here, and then rotating around the y-axis is going to be different than rotating around the y-axis and then around the z-axis. It'll lead to a different result. So we can compose all these together, but the order in which we do so then does matter. And then the other thing that we note is when we start to compose all these transformations together, we kind of lose, I call it sort of introspection or explainability of the matrix. It becomes much harder to look at the resulting matrix. Once you multiply 4 of these with 3 of these, with 2 of these, with 1 of these, it becomes much harder to look at the matrix, the actual values in our matrix, and say, well, here's what this matrix is doing. It becomes much harder to look at that and know because it's not necessarily all going to be invertible at that point to say, here is the exact transformations that are happening here. But by and large, one way to think about it is that the math does work, that you can do a scaling followed by a rotation, and in multiplying those two matrices together in the correct order, you wind up with a resulting matrix that gives you those two operations. And we saw that because we were rotating in 2D a square around its center, and we wound up getting the result we hoped that we would get here. So another way to look at this kind of flow diagram is this is all still effectively vertex shading. So this is maybe kind of an expansion or a zoom in of that one stage of our geometry stage of our logical rendering pipeline. You can also think of this as all being stuff that potentially gets done in my vertex shader itself. As a design decision we made, which I think is the correct one in terms of how things are done in practice today, we take that final step of the viewport transformation and we do not do this one in vertex shader, but one could apply a viewport transformation in the vertex shader. And similarly, this is a design decision that some of you will get to make yourself because we don't make it for you, is you can choose whether or not to do the perspective transformation in the shader or as potentially a separate piece of fixed function hardware to do the perspective transformation here. Part of that is we don't necessarily know, how this would be done in practice. I could imagine a driver for OpenGL for a particular piece of hardware that as you specify certain viewport information, it actually kind of auto-generates equivalent extra shader code to do that transformation. Or it could also be a piece of fixed function hardware like we've implemented it. So otherwise though, this is kind of just an expansion of that geometry stage. How do we go from our geometry that we specify in our OpenGL application, our X, Y's, and Z's, to pixel locations corresponding to something in our frame buffer. So we could work bottom up or we can work top down. Because we kind of understand that last stage there, I thought it'd be better to kind of work top down here, where you start with the specification stage, which we kind of know already and specify our vertex buffers and we do vertex fetch modules for them. But in terms of how we are specifying things, currently we're kind of taking it on an article of faith that if you specify everything in the range -1 to 1, your hardware will work. You'll get something that's valid here. Well, we're not going to have to make that assumption any longer once we implement this. Generally, when we have an object, we're going to specify it in what's just referred to as object coordinates. X, Y, Z, typically 1 for the W here. And whatever those values are, and this doesn't say per se what those values will be, it's going to be whatever is most natural or appropriate for that particular object. It doesn't say anything. Other than that, that's not what we've been doing currently, right? We've been assuming, to the extent we're specifying object versus just a few triangles, we've been assuming, well, 0, 0 is the center of the object and everything is relative to that in the range of -1 to 1. We're not required to specify our objects in that range. That is just what we have because we didn't have all of this hardware in place and didn't want to have to deal with it until now. In general, you should specify your objects in the coordinate system that makes sense for that particular object. And the goal there would be to make life easiest for those who are actually doing the modeling. Again, that's not a single triangle, that's now a seal or a building, or what are the examples I have here? A tall skyscraper-like building versus some molecular structure we wanted to visualize. Those should be specified in their own object coordinates. This doesn't say at all anything about like the units of those object coordinates, but the claim I'm making here is that it may make sense when we specify in one scene a building, tall building, and another scene some molecular chemical structure here, that we may want to use different values, a different object coordinates for one versus the other. Why would that be the case potentially? Why do you think? Ignoring maybe even the units aspect, although that could be thought of as part of it as well. Why would we want to specify a building using different object coordinates than we do for some chemical structure here? Sure, thank you.
I guess I would think about the units as, I guess when you're designing a building or something, you might design it using feet or something, and there'd be like tens or hundreds 4 different sections.
Right, so there's a scale issue to begin with, right? I guess it would also be, the modeler is the person whose job is to come up for the geometric representation of both this and this. We haven't done a lot of that this semester. You can take whole separate classes that's all about modeling 3D geometry, and you learn how to do that using either CAD tools or rendering support tools. But I think it would be fair to say that someone who is modeling this building is going to be having a different coordinate system that they're worried about, whether it's feet or meters, doesn't necessarily matter. That's going to be different in scale, and the things that are relevant to them is going to be quite different than someone who's doing molecular modeling. Now, then the question becomes, well, what if I want to render a scene in which there's a molecule on an office building? Well, that's going to probably look weird, right? That's okay, but there are different object coordinate systems, and then the next task is then going to be, if I really wanted to show single molecule in a building, possibly the molecule should be really, really small such that you don't really see it at all. But if it's a gigantic molecule in a building, then what we are going to then have is this modeling transformation, which again is just going to be a matrix, but it's probably going to be a scaling matrix of some sort for one or both of those objects, where we have a really tiny molecule in a really large building, and we want to be able to show them at being roughly the same size as each other. We would have to provide a scaling transformation to one or both of these objects, such that when we're now modeling the entire scene and we're now composing that scene of multiple different objects, we apply those transformations independently potentially to these to get a final value, which is the end, either translation, rotation, but certainly scaling of those two so that we can see them both and have them both be in the same frame at the same time. When you're thinking just in terms of triangles, that doesn't necessarily seem especially meaningful. But if you're thinking about now I want to actually have an office building, and I want a plane flying near the building, and a people down here in the building, well, you're not going to model the people as being exceptionally tiny, just like you wouldn't necessarily model this as being exceptionally tiny. But depending on where the person is going to be, or what we care about with regards to the molecule here, you're going to have to do some sort of scaling of the other objects in your scene, such that they make sense when put together in a single world. So that's our input to the viewing transformation pipeline. It does not have to be in that -1-to-1 range. That is our limitation because until very recently we weren't doing any of these transformations in hardware. So to the extent that you were doing those transformations, you were doing them yourselves when you were specifying your geometry. You were saying, here's my triangle and it's this size, and if I want a smaller triangle, I have to specify a smaller triangle. But in general, you don't have to do that, right? You specify the single building that you're interested in, and you get to decide after you've specified it in those object coordinates, how big or small do you want the building rotated, do you want it moved around. You do that after you've specified the object itself. So those are the object coordinates. The end result of the modeling transformation is you have that object and all objects in the so-called world coordinates. That is your common coordinate system for all the models in a scene. Again, the molecule and building example doesn't make nearly as much sense, but person and building perhaps, right? We have a model of a person, we have a model of a building. No matter what kind of level of detail the models were for each of those, after applying those individual model transformations, you should now have a common coordinate system for all the things that are going to be in the scene. So there's some scaling of the person, there's some movement of the person, there's some scaling and movement of the building. The end result is now you have a single coordinate system for everything that you may want to have in our scene. What then happens that we're going to talk about here is that the end result of both the modeling and the viewing transformation is you take all those object coordinates, translate them to what they should be relative to each other in a single world, and now you then translate them again relative to where you're going to be viewing the scene from. We have our person near our building for which we've specified the geometry and we've translated and scaled and rotated things. But what that final result's going to look like then has to go back to this, right? Not entirely just where we've specified all of our geometry, but where are we looking at the scene from? From what angle, what type of camera as well, but what angle we're looking at the scene from should then finally dictate what kind of transformations are happening to our input geometry here. That's the so-called I, or the other term you'll hear is just camera coordinates. Those are the same in some sense as the world coordinates, but they're from the perspective, from the angle of where the camera is going to be located. Here's one way to represent that. So we have our coffee cup, and it is part of a scene. Coffee cup is the output of a CAD model of a coffee cup. Oftentimes, if it's a CAD model, what will be the result is you'll be centered at the origin somewhere. When building a CAD model, there's no point in centering it anywhere else. But the coffee cup is not necessarily the center of our scene at all times, right? It's the center of its own object coordinates because it's just relative to somewhere we're starting as a baseline for representing that object. We are going to take that object in its object coordinates and we're going to determine, well, it's actually one of many objects in the scene. And it's going to get translated, perhaps it's going to be made larger, perhaps it's going to be made smaller, and it's going to be relative to other objects in the scene composing a desk or a table that that coffee cup is getting put on. That is all the objects in the scene then getting translated via that modeling transformation into world coordinates. And then finally, we then have to determine, this is our eye or our virtual camera model here, where are we actually looking at the scene from? Because the end result of what those coordinates need to be for all these objects are all going to be relative to where we're looking at the scene from. So that as we move the camera around, we're not really changing at all the original world coordinates of the individual objects here, but the end result is going to be different in terms of the final coordinates of where those objects in the world are relative to where we are looking at that particular scene. Walking through the rest of it just kind of quickly here, then before we go into depth of them. So we have our object coordinates into our world coordinates with a modeling, then following a viewing transformation. The end result is the coordinates of the system relative to where the camera is. There is then a camera-specific transformation that happens that translates it into so-called clip coordinates. If there is an end result where our W value is not equal to 1, we need to kind of correct for that transformation. That'll be seen as having things that are actually further away from the camera appear to be smaller. So there'll be some division based on what the resulting Z value is ultimately going to be. And then finally, after we've done that, we have our so-called clip/normalized coordinates here. Then we're back to our 2 by 2 by 2 box at the origin, our -1 to 1 range of values. And we have that for a couple of different reasons. Historically, we have that projection converting everything into a box at the origin of 0 of size 2 by 2 by 2, so that when we do that clipping of our objects in a scene, it can be a relatively straightforward operation. Anything of a value less than -1 or greater than 1 in any dimension is going to be at least partially clipped. And then only at that point do we then do our viewport transformation to take those values from -1 to 1 and convert them to depth values as well as our pixel coordinates corresponding to what our depth buffer is going to need to be. This is trying to show one step of what happens post-projection, but it doesn't really show the rest of what's happening there. Let's go back to the camera analogy and what that corresponds to with our synthetic camera analogy. I want to take a photograph of something. It's called a proper, still frame photograph of a scene, of an object, of something happening in the world. What are the steps that are required? You set up your tripod and point the camera at the scene. If it's not a tripod, you put it somewhere or you're holding it at a particular angle. So whether it's a tripod or not, you're setting up your camera and you're pointing at the scene that you're interested in taking. You may then also have to arrange the scene to be photographed. Well, actually, you're too far away. You move a little bit over, or you move further in the back. You're arranging the scene. That's the equivalent to our modeling transformation that we have here. We are then also going to have to choose. Sometimes the smartphone cameras do this for us, but in conventional cameras, we then would choose our camera lens or adjust the zoom of our particular scene. That's going to correspond to our projection transformation here. And then finally, even after we've taken the photograph, we have to determine, okay, I want to actually have this displayed, I want to have it printed, I want to determine if it's going to be blown up as a poster or displayed very tiny here. That's the closest analog to our viewport transformation with conventional photography. You have the image, you then determine where it's going to actually appear at the end of the day. That's the equivalent of a viewport transformation here. At that point, you can stretch and shrink and do all sorts of those linear transformations for it as well. The end result, when doing our positioning of both myself and where the camera is going to be, our tripod for our camera, as well as positioning where the objects are going to be in a scene, the end result is going to just be a matrix, referred to as the model view matrix, that transforms where the origin is relative to our objects in our world for our particular scene. and I was mentioning this on Thursday, but now let's see what this looks like in practice, is that while as we look at the breakdown of what's happening here, these are kind of separated into taking objects, converting them to world coordinates, concerning where our camera is, translating those world coordinates to our camera or our eye coordinates here. And this is seen as a modeling and a viewing transformation. That is still logically correct what is happening. The end result is a single matrix, the so-called model view, and that's all that means. The modeling and viewing matrix combined together that transforms where the origin is from our local model coordinates to our world coordinates, now to where we're seeing things from our camera's perspective. Whether you think of those as being 2 steps or 1 step doesn't necessarily matter. There are some shading techniques that require doing modeling separate from our viewing, but the end result is a single matrix anyway that gets applied to our geometry in the scene. We already looked at last week a couple of like the GLM functions that allow us to generate those matrices without having to, for want of a better word, think about it too much in terms of how we're setting up those individual matrices. Again, as you are doing more and more of those transformations, it gets harder to reason about the individual elements in the matrix that gets generated. So we tend to use these kind of functions. The old school OpenGL way of doing it was calling GL translate, followed by GL rotate, followed by GL scale. The current way of doing it is effectively to call a third-party library that does those equivalent operations for you that return the corresponding matrix, but they're just doing matrix math along the way. Again, each individual translation, scaling, and rotation, we can set the matrix ourselves because it's exactly as what was given a few slides back. Only once we start to combine all of those together, it gets a lot harder to say, what should element 2, 2 of this matrix be once we've done 15 transformations? It's much harder to reason about that from first principles, so we tend to compose the transformations step by step. This demo, which is using old school OpenGL, but I think kind of gets the job done, is meant to illustrate that equivalence between modeling and viewing. I break them down into 2 separate steps here, right? One is, if we just want to think about translation to begin with, one is, where do I want to place my coffee cup relative to the rest of the world? The other one is, where do I want to place my camera relative to my coffee cup? And logically, those are 2 different things that we are doing. In terms of the resulting matrix that gets computed, they are identical, right? And in terms of OpenGL calls here, this is a factual statement in terms of GLM calls here, that the function that allows us to move and change our modeling matrix, GLM translate, or what used to be called GL translate, move an object 5 units away in the Z dimension. Push this coffee cup 5 units away, right? The units aren't meaningful at this stage, but push the coffee cup 5 units away. Versus GLM look at, which is place my, and we didn't talk about the actual definition of this, place my camera 5 steps in this dimension from the origin. Place my camera 5 units closer from the origin to the rest of the world. Those are equivalent. Do I move my object closer to the camera, or do I move my camera closer to the object? Logically, those are 2 different things. The physical analogy is 2 different things, right? You can't move the building very easily. It's much easier to move the camera. But in terms of the matrix that gets computed, they are identical. They both produce the same exact modeling / viewing or model view matrix, and the result is exactly the same. That's what's meant by, if you hear the term as I'm referring to here, modeling and viewing equivalence here. So I like this, even though it's using old school OpenGL, because it is basically just allowing you to play with the viewing model view matrix to see what it should look like, the end result of the scene should look like on a frame for that 3D view of a scene, and then separately kind of synthetically create a view of the world that allows you to see what is actually happening in practice here in terms of where the camera is being positioned. This is showing perspective transformation that we have not talked about in detail quite yet, but otherwise it's still perfectly fine in terms of seeing it here. You need perspective, otherwise when things are further away, there's no point. It looks exactly the same. But it's an attempt to view the camera's position relative to the object, or is it the object's position relative to the camera, and then what the end result scene is going to look like. And it allows you just to kind of play with those parameters here. So translation, we may be able to understand first. If I go GL translate or GLM translate to create the corresponding matrix, and I change my x dimension, so that's x, y, z we have here, those three parameters, and I change it from x value of 0 to x value of 3 or something like that, we would think of that as, all right, GLM translate, move my object 3 units over to the right in my x dimension. And 3 might be too large for this example. Let's stick to 1 here, because otherwise it's going to fall off the scene entirely. And that's what happened, right? The car, we can move it back. The car, as we're incrementing our GL translate, is moving a unit to the right. Again, there's perspective here. It's why it doesn't look like it's just like straight shifting. I don't think I can change the type of camera here. Not in this example. There's other ones we can. We can change the object here if we want to make it a person, a distant relative of mine is what we're viewing here. GL translate, moving it to the right. But let's look not on the right-hand side here. Let's look at what the equivalent thing is happening on the left-hand side here. Maybe I'm belaboring an obvious point. It's not showing us the matrix, but the matrix is the same here no matter how we visualize it. Are we moving the object to the right, or are we moving the camera to the left? The answer is both, or neither, or either, right? And the example being, if we're looking at the world space view, which is just an attempt to see what's happening with where the camera's positioned in our scene here, we are actually moving it to the left by setting GL translate of that positive value here. The same goes for all those operations as well. Let's recenter it here. Let's now scale it in the x dimension, right? That's our stretching of the x dimension. If our x value is 7, when we scale it with 2, it's going to be a value of 14, right? So things should look stretched out from what they were when the object itself was specified. And that's exactly what's happening here. This is me over spring semester, right? Getting scaled in the x dimension, and I haven't gotten any taller, but we can do that as well. From our object specification, the human here, the objects didn't change, right? Whatever geometry was specified, the vertices, our vertex buffers for that particular human here have not changed. They were still specified once. The buffer was loaded exactly once, and we said draw arrays on that particular buffer here. The only thing that's changed is the matrix we're applying to it, and we're scaling it in both the x and the y dimension. Now look on the left-hand side as we do that same scaling here, and we can think of that scaling now being as shrinking the projection plane of our camera relative to the rest of our world. So are we shrinking our camera's projection plane? Are we stretching the objects? Doesn't matter. We're doing both or either, right? It's generating the same matrix. The same, although it's a little bit harder to see in this, would be the same for our rotation as well. When we're rotating in the x value, our z should stay the same here. And it looks like, yeah, I'm rotating this object around the y-axis. But now when we look at them at the same time, look at what's happening from our so-called world space view. Again, this view on the left is meant to be for like illustrative purposes. This is never ever part of our render. This is the writer of this application creating a whole separate scene and visualizing what would happen for these corresponding transformations. But it's a way to kind of get a more intuitive view for what's happening when we do those rotations. Are we rotating the object or are we rotating the camera? Kind of both, right? We're rotating the camera around the object or the object around its own axis here. That one's a little synthetic because, once we move the camera so that's kind of inside the object, that would be in the z dimension. Well, he's hollow. Why would you waste triangles on the inside of him? And then we do that rotation. I guess it's, now it is really equivalent because now they're effectively on the same origin. So now the rotation is the same as the rotation of the other. But in general, the idea here is to kind of show the equivalence of that modeling and viewing. That I think translation is probably the easiest one to reason about. Are we moving our object? Are we moving our camera relative to the object? It doesn't really matter. But that's that kind of first step, that we have our objects. And it's likely to imagine a scenario in which we have an F-16 jet, in this case, for this example, they're all in the same coordinate system when they're specified. They don't have to be, though, right? Our jet could be this really massive model where how it was generated, for the way in which it was generated, the dimensionality of the actual geometry is way bigger than it was for the person. And the only downside of this example is we really can't see both of them simultaneously. But you would then have to have a scene where the person, is very small relative to the jet, right? Because you want to have the person inside the jet, right? And so we would be applying those modeling transformations independently for all the different geometry we want to have in our scene. And then we have our camera, which is looking at the objects in our scene to generate a final model view matrix for it. Then the next step after we do that modeling and viewing is the so-called projection transformation. I'll introduce this now, but we'll wait until Thursday to really go into the messy detail. It starts to get a little messy, but I think at the end of the day, you're going to have API calls or GLM third-party library calls that give you the same kind of functionality, and it generates a matrix that, if you like the way it looks when you've viewed your scene in such a way it's sufficient for your purposes, it is still just a matrix vector multiplication at the end of the day. We'll go until we run out of battery life here today. The concept of what a projection is, conceptually, is that when we project something, we're going from m dimensions to n dimensions, where m is greater than n. For our purposes, projection always means going from 3 dimensions down to eventually 2 dimensions. When viewing a scene and when choosing a camera, there's effectively a fundamental choice that we make. Whether we want to have an orthographic or a parallel projection of a scene, or whether we want to have a perspective view of a scene. I've seen some sources that talk about one being more, correct than the other. Correctness or one being better than the other only has meaning when talking about trying to represent what like a human sees, because our own eyes use perspective in terms of it's a camera and it has a focal length and we have a perspective transformation that happens. But one is not better or more correct than the other in any other real sense of the world. The difference between orthographic, when you hear that word, think parallel projection. Things that are parallel in the object maintain that lines of parallelism when we actually project it to our final image, to our final screen that we have here. With a perspective transformation, there's a convergence that happens. That our lines that were straight to begin with are still straight, but we lose our lines of parallelism that we have here. Effectively, you can think of the orthographic or the parallel projection as being just dropping of our z coordinate system. That's one way to do it. There's other types of orthographic projections we make that eventually will be dropping the z, but that's one way to do it. I specify all my geometry, I just drop the z parameter. Even if for our purposes we don't actually want to drop the z parameter until later because we may want to do depth buffering and things like that. But effectively we ignore and just remove any instance of the z value that we have here. Whereas in our perspective projection here, we instead kind of divide by z. Another way to think about what is happening when we do perspective versus orthographic view, and you can think of focal length of a camera if you have any interest in taking photography, is when we're doing perspective viewing of things, objects that are further away should appear smaller to us. And that's effectively what's happening. We divide by z. Given how much larger a z value this object has in the far distance versus this object that's very close to us, it should appear smaller, the objects that are further away. Right? There's a cup in the 6th row of this classroom, there's a cup in the 1st row of this classroom. They're roughly of the same size in reality, but from my visual perspective from here, that one seems significantly smaller than the one that's up here. In reality, in terms of how we specify the geometry, they're the same exact size. The projection transformation we wind up applying